So we're now going to consider integrals of this form. We've got 5x times e to the ix integrated over all x. So they can be done using the residue theorem as long as we can use Jordan's lemma. So we basically, that phi of z needs to go to 0 as z tends to infinity for the argument of z between 0 and pi. This applies for a greater than 0, and we use the usual semicircular contour with radius r, which then goes to infinity. If a is less than 0, then we use a semicircular contour which goes below the axis. And then Jordan's lemma is really the same thing, except we just change this from minus pi to 0. Okay, so why is this useful? Well, you might recognize this as the Fourier transform of phi. Or I should say one more thing, that phi has to have a finite number of poles above the axis. It can't have an infinite number. Okay, so yes, this is a Fourier transform of phi. Also, if you want to evaluate integrals like this, we've seen something similar to this a bit earlier in the course. If you want to evaluate, for example, phi times cos ax, then that's just the real part of phi times e to the iax dx. And if you want to evaluate phi times sine ax, then that's just the imaginary part of phi e to the iax dx. So in the end, what we do is we consider, for all of these cases, all these three cases, we consider the contour integral of phi z e to the I a z dz around this type of contour if a is positive, and this type of contour if a is negative.